Hello, everyone. My name is Aayush Jain, and I'm a new assistant professor joining the computer science department at Carnegie Mellon University. This is a slide which contains some basic information about me, my research area, my office number, my email, and so on and so forth. So my area of interest is cryptography, and it's a field, very broadly speaking, it's a field that systematically leverages or utilizes or harnesses um, hardness that exists inside naturally occurring computational problems such as factoring or discrete logs, so on and so forth, to build useful stuff. And just to give you some examples, you might have heard some buzzwords such as zero-knowledge proofs or multi-party computation, homomorphic encryption, especially in this age of cryptocurrencies and cloud computation. So all these buzzwords are actually concepts that lie within the fold of cryptography. And very lately, or in fact, for the past few years, I have been fascinated with this question. The question is, can we protect our programs, the programs that we write? In fact, the secrets that we use to build those programs while ensuring usability. So just to make the question clear, we all write computer programs, and writing these programs typically require some sort of new idea or technical insight or some kind of novelty. So the question we are asking, is it possible for me to write those programs in a very specific way such that the novelty itself remain hidden or protected even from someone who gets to see the code in the clear? Okay. And just to make the things very precise, what I'm looking for, and this question is called as program obfuscation, was posed way back in 1976. And to formalize this, what we're asking for is a compiler, which I'm going to call as obfuscator. What does this compiler do? It takes as input a source code or program. You can think of it as a program written in some high-level language like C, or you could have, think of it as some program in some mathematical model like circuit or a Turing machine. Takes as input that program, outputs another program. Now this program has essentially same input output behavior as the initial program. It also has comparable efficiency, so it's at most polynomially slower than the initial program. But what I really am really looking for is that now this program reveal minimal information or as minimum information as possible about the conceptual flow of the program, or like the internal working or implementation of the program, and what conceptually it's actually doing. So that part, this notion is supposed to tell. I'm not going to formalize what this means. There are definitions in like cryptography. I'm not going to touch upon that, but just think of it something which lets you use like compiler, which turns your program into another program, which has the same behavior, input output wise, but other than that, doesn't leak information about what actually the program is supposed to do, right? So this is the notion that we are looking for, and I'm sure if you think a little bit about it, it's very easy to find lots and lots of applications. One of the applications that I really like is this from the domain of machine learning. As you know, machine learning has been like so instrumental, and it has really revolutionized our society with such amazing applications. One of the dream applications in this area is to automate medical diagnosis, right? So it's possible that there are several hospitals, they see a lot of cases on day-to-day basis. So it's plausible that we can run some machine learning algorithm to come up with a classifier F. What does this classifier do? It takes as input a scan or a test result and outputs whether it thinks there's a disease or not. In future, it is completely conceivable that we might be able to build such classifiers with such unbelievable levels of accuracy. And if that happens, we'd like to make the code of this classifier accessible to as many people as possible, especially in areas where there's lack of proximity to good doctors. But that's where we run into issue. If you make this classifier public, then often the way these classifiers are written, reading them actually and examining the code of the classifier can reveal a lot of sensitive information about the training data set. And then because of that, it's actually simply against the law, because like you're going to violate sensitive information about the cases that the hospital examined, right? But turns out if you had obfuscation at your disposal, what you could do, you can simply obfuscate the classifier, and obfuscation is going to protect, um, we're going to protect as much as possible the sensitivity of the training data set that you use. At the same time, it will let you, because it doesn't change the functionality, it's going to still let you use the code as if there was no obfuscation involved. And so this provides a candidate pathway to solve this problem. And this is just one application, but even theoretically, it's been really instrumental or central to cryptography. The notion of obfuscation that we study, called indistinguishability obfuscation, has given rise to a broad generality of primitives in cryptography. And that's why it has a central position today in cryptography. And I'm going to call this notion IO, which is short for indistinguishability obfuscation, right? So this is obfuscation. Now let's ask what are the things that are known about it, and what are some of the main open problems in this area. So it turns out up until 2013, we didn't even have a candidate construction to build this. But this changed in 2013, and since then there have been many, many constructions. But up until recently, unfortunately, all known constructions were kind of on shaky foundations. They relied on hard problems or problems that haven't been studied for a long time. So our confidence in those assumptions were a bit shaky. This changed recently with a joint work with Rachel Lynn and Amit. In fact, two works where we showed that you can construct this notion, and we gave a construction which is as hard to break as several long-standing hard mathematical problems that are widely believed to be hard. So that was the key contribution. This work in 21 actually won the best paper award at Stock, and settled at least the feasibility aspect from well-studied hard problems. Okay. So while the feasibility kind of is answered, there are so many things that still need to be done. We are still at the very initial stages of this problem. And in my research kind of focuses on addressing, current research focuses on addressing some of these main open problems in the area. So, for example, today we know only very, very few, despite this question being open for a very, very long time, we actually know a very few number of ways to construct IO. And so we need to find out more ways to construct IO, and that's one of the questions. Secondly, since we know very few ways, these ways are actually also turn out to be incredibly complex. If you were to write it down like this as a scheme, the kind of parameters that we get, they're astronomical. They're still polynomial time, but those polynomial itself are huge. So that's why they are infeasible to implement currently. Making progress on this question on the practicality or implementability aspect is a very important question in this area. Further, we need to protect our schemes against looming threat of quantum computers. If they see, if you're able to realize quantum computing, we like to protect our cryptographic schemes against the threat of quantum computers. And that question is actually not very well understood today. And so making progress on this is also very important. And finally, currently what I'm thinking about is also understanding if there are new mathematical structures which are typically haven't been explored in cryptography, which are simultaneously hard, which are structures which are hard problems, but at the same time have enough structure in them so that they can give rise to something as powerful IO. So there's a question that involves aspects of both the study of algorithms as well as study of cryptographic usage of computational problems. With that, I'd like to thank you.